provide the basics of section 6.3 with a focus right now on the sine and cosine functions. We'll talk about tangent a little bit down the road, but right now we're going to focus on the graph of the sine and cosine function as well as the assorted transformations thereof. What I asked you to do in class, I gave you another copy of the unit circle, and what we basically did very quickly is using the unit circle, we kind of filled out a very short grid for the sine of t and the cosine of t. T now becomes our independent variable, y will stay as our dependent variable, but we're going to use time just because it's something that, because of the nature of these functions, periodic nature of these functions, and the way that these things occur in real life, time serves as a very nice independent variable. We worked through our unit circle, we got these different values, and then I asked you to go ahead and just basically graph y equals sine t, and as you'll see below, y equals cosine t. I'm not going to belabor the stuff that you did on the unit circle, but I want you to just focus on the results. You received basically a wave pattern, which is what a sine and a cosine are. It's a very constant. It's a periodic function, which we'll talk about in one more second, but it has a very predictable pattern and a number of interesting characteristics, one of which is the period, how long it takes before the function repeats itself. And what I've done here in the graph, I've highlighted 1 period's worth of data, so to speak, on our graph. And I've kind of made this, I'm going to call it my home period. You'll understand why when we start talking about transformations. But I kind of use this viewing window of t running from 0 to 2 pi in both of these graphs as just kind of my first look. Where would I look at and just kind of home in on these two graphs? The answer is the basic parent functions, 0 to 2 pi is where my eyeballs are going to be set. Now, when looking at this, we saw a bunch of characteristics, and what I'm going to do, I'm just going to flip to the next page and point out, I don't have color copier at home here, so I just had to kind of do a hand version here. I rewrote y equals sine t, y equals cosine t, and just again kind of highlighted that main drag, that main period that I want to focus on. So with that in context, I'd like to just look at a couple of items that we've talked about up here. We said that there is a period for these two functions. A function's periodic if it behaves in a repetitive manner across every interval of a set by a space that is consistent. That value we call the period, p, and what we know about the period, it'll be such that f of x is equal to f of x plus p. That's a generic version. Maybe for what we're doing, I could say f of t equals f of t plus p. If you recall, one of the things we talked about, the sine function and the cosine function happen to be coterminal every 360 degrees, or 2 pi radians. Our graph here works in radians, which is going to be very constant and consistent for these functions. Radians is our unit of measure for the dependent variable. But bottom line, the sine and cosine have a period of 2 pi. These graphs also have a number of nice characteristics. They have a midline. That's the value that kind of serves as the vertical center of the graph. You'll notice this midline happens to be at y equals 0, kind of our default for our parent function. What do we notice? The max value happens to be at 1, the min value happens to be at -1, and that value of y equals 0 serves to be kind of a centering value. That's what the midline is. Provides vertical symmetry. Now, when you go from the midline up to the maximum or the midline down to the minimum, that absolute distance is called the amplitude of the function. Amplitude is a measure of variation from the midline. How high do you go? How low do you go from the midline? And again, it's always expressed as a positive number, an absolute number. A couple other things that are interesting about these graphs is they both possess a certain type of symmetry. You'll notice if you look closely enough that the sine function happens to be an odd function. The sine of x is equal to the negative sine of negative x. And we'll come back and you'll look at that in a little bit. You'll notice that the cosine function happens to be an even function. Sine of t equals sine of negative t, a reflection over the y-axis. And if we look at this graph, we would see that's exactly what's happening. I could take this piece, flip it over, I'd wind up perfectly just right there. With the sine function a little bit differently, it reflects over the good old line y equals, in this case, y equals t. It's an odd function. Another very interesting characteristic, and this is something that I think is going to be very important. I've highlighted it down at the bottom, but you can see it written here as well. There's a certain pattern that we run through over the period. That pattern depends on what function you have, but it's a very consistent pattern over the 0 to 2 pi. Let's talk about it. With the sine function, notice as I run through the period, there's kind of just what? I hit 1, 2, 3, 4, 5 points, so to speak, as I go from repeating the pattern. I start at my midline with the sine graph. I go up to the max, return to the midline, hit the minimum, back to midline. And you'll see it down here, the sine pattern. When I draw a default sine pattern over its base period, 0 to 2 pi, how do I draw it? Start at the mid, go to the max, return to the mid, hit the min, finish at the mid. And at the cosine pattern, it's a little bit differently. What do I notice about the default period, 0 to 2 pi, and what that cosine function does? Starts at the max, hits the midline, goes down to the min, returns to midline, finishes up right back where it started at the max. That's the nature of a periodic function. And so what you'll find is if you understand these patterns, that the sine function, if you kind of want to draw its normal period, and then for that matter, as we'll see, any transform period, midline, max, midline, min, midline is the perfect way that you'll draw that. Cosine, you'll follow this pattern. So these are the general ways to verbalize the sine and cosine parent function patterns. Let's start talking about some transformations. And the way I set this up is just an intuitive analysis of transformations. We'll get a little bit more formal in a bit. And so what I asked you to do is take a look at these different things that we're going to do and see what's the impact on maybe the period, the amplitude, the midline, when I go to these new functions or these impacts against our parent functions. When we have a vertical shift, we came to the conclusion that my amplitude stays the same, my period doesn't move. All that happens is my midline moves up and down. My max and min do change. They have to because the graph moved up, but the amplitude does not change. The only thing that truly happens with a vertical shift is our midline moves. With a horizontal shift, you'll hear that referred to many times as a phase shift. Think phase of the moon, phase of the tidal pattern, something of that nature. When does it repeat its pattern? That's kind of what a phase is. In any case, a horizontal shift, all that does is it takes the graph and moves it left or right. And in the context of what we're doing, what we can say is, all it really does is it changes where we'll start to draw our default period. We're going to usually start drawing at t equals 0. Now when we have a shift and we're going to draw kind of our base period or whatever for the transform function, we're going to start drawing by shifting horizontally, either left or right, just depending on what the actual shift is. When we have a vertical stretch or shrink, what happens? A vertical stretch and shrink does nothing more than change the amplitude. Period stays the same, midline stays the same. Just the amplitude, how far up from the midline, how far down from the midline will we go in absolute terms, is what the change in amplitude will do. A horizontal stretch or shrink, we come back and if we look at our two graphs, what would we be doing? Pushing in is what a horizontal shrink, horizontal stretch would push it out. What do you notice? A horizontal shrink is going to increase the period. The thing's going to repeat itself more. Think about this. You're just kind of folding in all these waves. Here, you're stretching them out. It takes longer for the pattern to repeat itself. You're going to increase the period. That's what a horizontal stretch or shrink will do. And finally, a vertical reflection. Again, let's just go back to a couple of our base graphs. All a vertical reflection does is flip what? Flip the graph over the y-axis. And so think about it. What it really does doesn't change the amplitude, doesn't change the max and min. It maybe changes the coordinate where the max and mins happen, certainly in terms of the t coordinate, but it doesn't change any of those y values. And if you flip this graph, what would you realize? Hey, it's just my drawing pattern that changed. I still start at the midline, but if I flip this graph, I would do what next? I'd go to the min. I'd return to the midline, I'd go to the max, finish at the midline. So all a vertical reflection is, in other words, putting a negative sign in front of y equals sine t or y equals cosine t, all it does is it changes the drawing pattern. So be familiar with that here, and if we flip this one, what would happen? Well, my midlines would never change, it's just the max and mins would move to a different spot. What would the bottom line be? What would the drawing pattern be for a vertical reflection of the cosine function? It would be negative cosine t, number one, but what would happen? I'd start at the min, hit the midline, go to the max, back to midline, finish at the min. That's all a vertical reflection of the cosine function will do. So the bottom line is, down here we have a positive sine pattern, we have a positive cosine pattern. Those are the things already highlighted. But we can build a negative sine pattern and a negative cosine pattern very, very quickly. So let's just do it. Make sure you get this down. A negative sine pattern, mid, min, mid, max, mid, excuse me. Mid, min, mid, max, mid. A negative cosine pattern. All you got to do is everywhere you see max and min, just change them. Min, mid, max, mid, min. So these four drawing patterns will be very, very helpful to us. See what type of function you have. You're going to have one of these four patterns, and it's going to give you the exact way in which you can start to draw that wave. All right, so let's be a little bit more formal, and we're going to start to try to put all these pieces together. Just like we had in chapter 2 when we were doing transformations of basic functions or whatever, we have transformations now of trigonometric functions. And what we'll do, and we're using x as a variable just to be consistent with some of the things that were done in the book, but this could be t just as easily. We're going to have f of x equals plus or minus a times the sine of, and look at this, sitting in brackets, b times in parentheses x plus c, close parentheses, close bracket, plus d, and the same thing for the cosine. Same thing, all we did is just interchange cosine as opposed to sine here. If you got a standard parent function, what would you know? A is equal to 1, you got a plus sign up front. B is equal to 1, C and D would be equal to 0. And if that was the case, you would wind up with f of x equals sine of x, f of x equals cosine of x. So let's start working with some transformations. Y equals sine t plus 4. What is it? It's a positive sine pattern. The amplitude does not change. The midline changes. The period does not change. All that happens is what? The midline moves up 4. Does the max change? Yes, it does, because now that we got a new midline, our max also moves up by the same amount. So the max, what used to be at 1, is now at what? 4 plus 1. Remember, the amplitude stayed the same at 5. Our min is at 3. And we know what type of pattern to draw. We can just start at 0 for our value at t, run the 2 pi, draw our little shape. It's a positive sine shape in this case, and we'll be in perfect condition to build that. Y equals 2 cosine t. Period stays the same. Midline stays the same. The amplitude doubles. Midline still at 0. The max now, it used to be at 1. Well, the amplitude has doubled. So when I'm at the midline, I used to just go up 1 unit or down 1 unit. Now I'm going to go up 2 units or down 2 units. I'm going to draw a positive cosine pattern for this one. Putting a couple pieces together. Y equals 1/2 sine t minus 2. The midline is going to move down 2. The amplitude is now going to be, it used to be 1, now it'll be 1/2. The amplitude was cut in half. So if we think about it, I'm going to have a mid of y at y equals negative 2. My amplitude is 1/2. I'm going to have a max at negative 2 plus 1/2 at negative 3/2. My min is going to be at negative 2 minus 1/2 at negative 5/2. Again, do I have everything I need to draw this pattern? I really do. I know that I kept my period the same, so I would start drawing at 0 for t. I'd finish drawing at 2 pi for t, And again, I'll follow my shape. Let's keep going. Same pattern, same structure, now some different pieces. And let me do one more thing just for a second, kind of iterate back some of the pieces we've done before. All of these, notice what? Any of the impacts that we had take place outside of the function. These are all vertical impacts. So just make note of that. What we're going to see now on the next page is what's happening. We have inside the function impacts here. What's our first one doing? We're taking the sine of the angle x plus pi. What does the plus pi do? Do? It shifts us horizontally. And in this case, since we're plus pi, it's a horizontal shift left by pi. Did the period change? No. Did the amplitude change? No. Did the midline change? No. All we have to do is take the sine graph. Go back and we can look at one of them. Take this sine graph and shift it over by an amount of pi to the left. So this black part, instead of starting at 0 and finishing at 2 pi, what would it do? Shift it left by pi. It would start at negative pi. It would finish at pi. That's all I do. I could pick up that black piece, move it pi units to the left. That's the only change that would happen. Cosine 2x. This is inside the function. And here's the key thing. In here, good way to describe it is I don't need as much x to get a certain value. It's kind of a funny way to say it, but it's a nice way to think about it if you pull back and just stare that down, what I said for a second. But the bottom line, let's just translate this. This is also a inside the function impact. It's a horizontal impact. And specifically, what this does is it changes the period. And more specifically, for a cosine or sine function, anytime you see a factor inside the parentheses like this, you'll find that your period is equal to 2 pi divided by, in this case, that value of 2 is going to be your value of b in the equation above. So what happens with this? Amplitude same, max min the same, midline the same. Where you start drawing, the beginning part for drawing a period stays the same. Where you finish drawing, that's going to be different. Why? Because the period is new. In this example, b is equal to 2 from our generic structure. The new period becomes 2 pi over 2, or pi. So what's that going to tell us? Well, if you think about it, it's doing what? It's compressing this thing. What will happen is this little graph, that little black part, it's going to still start at 0, but the period is now pi. I'm going to draw this whole pattern, used to run over here. I'm going to take that whole black thing and I'm going to squeeze it in. And it's going to do its whole course. It's going to run a whole period in pi units as opposed to 2 pi units before. That's what's happening here. And we're going to work a complicated problem down at the bottom in just a couple seconds that will put this all together for you. Here's another example, however, that's nice. Just like we put all our vertical impacts together, we're going to put our horizontal impacts together. And what I want you to be careful with when you see something like this, you want to make sure that in your parentheses, the sign of whatever lives in here, make sure that the x does not have a factor in front of it. You want to make it of the form b times, in parentheses, x plus c. So I'd like you to look at this 2x plus pi over 2 and do the following. I don't want a 2x, I want to see an x by itself. So 2x plus pi over 2, I want it to turn into something times x plus something. And what that means is take a 2 out. Factor out the 2 from both terms. What does that in turn do? This plus pi over 2, when I take a 2 out, becomes plus pi over 4. That's what I'll look like. And now, here's what comes out of this. 2 pieces will result. First things first, horizontal shift left by pi over 4. What else? Period changes. It becomes what? Again, just like before, our value of b is 2. 2 pi over 2 equals pi. So what am I going to do? And we'll do this with an example in a couple seconds so you can see all the different pieces. But what I would do is I would take this graph, I'm going to compress the period, so I'm going to have to draw this little black shape faster. I'm going to shift over negative pi over 4 to the left. My whole period, by the way, let's just do something. I'll make a mark here. My period now shifts to the left. My starting point for where I'll draw used to be at 0. Now I'll start draw. So I write sometimes start draw equals negative pi over 4. My period is pi. That tells me that my end draw equals negative pi over 4 plus pi, or 3 pi over 4. And so that's the result that I'll walk into by putting these two pieces together. Let's do a full-fledged example. Y equals 4 sine of 2 times t minus pi over 4 plus 3. Lots of different pieces here. Plus 3, midline, moves up 3, midline at y equals 3. And so what I'm going to do, in a second, I'll start dashing the graph so I know where my midline is and I can draw kind of around it. 4 is my amplitude. Amp equal 4. If my midline is at 3 and my amplitude is at 4, my max is at 3 plus 4, 7. My min is at 3 minus 4, negative 1. I can now go ahead and label my y-axis. And what I'll do very quickly, now that I got those pieces, I'm just going to go ahead and dash. It's not part of the graph. It's not an asymptote or anything. It's just a drawing aid for me. Next piece, what do I want to do? Well, negative pi over 4, t minus pi over 4, horizontal shift, right by pi over 4. I'm going to start drawing. I used to start drawing at 0. Now I'm going to start drawing at pi over 4. So I write start draw, t equals pi over 4. I'll go ahead and put a pi over 4 out here. 2, haven't accounted for that yet. That's my value of b. That is a horizontal stretch or shrink factor. It builds my period. And just like the other examples, just by convenience here, but my period equals 2 pi over 2 equals pi. What's that tell me? End draw equals pi over 4 plus pi, 5 pi over 4. Okay, now, one thing that we haven't talked about, but I hope you might start to see is what? When we draw a period, we have basically 1, 2, 3, 4, kind of 4 ticky marks that we draw through from the beginning. Start here, ticky mark 1, ticky mark 2, ticky mark 3, ticky mark 4. They are all of the same length. It turns out the length of these ticky marks, where I'd go ahead and label my axis, is nothing more than, think about this for a second, period divided by 4, correct? I'm going to run for a period. What am I going to do? I'm going to go through 1, 2, 3, 4. 1, 2, 3, there's my 4 ticky mark, and I'm going to finish. These are all symmetrical about each other. They must be separated, what? 5 pi over 4 is pi. So these little ticky marks must be nothing more than pi over 4 apart from each other. This is pi over 4. This is 2 pi over 4, or pi over 2. 3 pi over 4. 4 pi over 4, namely pi, and 5 pi over 4. My last piece, I've handled the 4, I've handled the 2, I've handled the minus pi over 4, I've handled the 3 with everything here. What type of drawing pattern am I going to use? Do I see a negative sign? Not in the least bit, and it's a sine function. So I'm going to draw the positive sine pattern. Positive sine pattern. What's the positive sine pattern? Starts at what? The midline. Where's my midline? It's at -3. What's the positive sine pattern do next? It goes to the max, which we know is at 7 on my next ticky mark. I return to the mid. I go down to the min, which is at -1 on my next ticky mark. And I finish where? Back at the mid. And all I have to do now is connect this lovely thing. And I am good to go. So there's a pretty complicated example. Let's put it all together one more time visually with what you see right here. What are the steps needed to plot a transformed sine or cosine function? Here's your generic function. I happen to use the sine, but you can interchange cosine right below. Just doing this to save ourselves some time. Here's the bottom line. D, I'm using capital letters here too, just for the visual or whatever. D controls the location of the midline. If you see a plus D, you know exactly where to put your midline. Either plus D, put it up in positive territory, minus D, your midline is somewhere in negative territory. A defines the actual amplitude. How high up from the midline you go, how far down from the midline you go to hit your max and your min respectively. C, either T minus C or T plus C, controls the adjusted period. I say it controls where you start to draw. That's a better way to say it. Adjusted period, really what I'm saying there is where do you start to draw. If you see a minus C, controls your phase shift. If you see a minus C, that means you're going to start moving C units to the right from 0, and that becomes where you draw. If you see a T plus C here, what are you going to do? Instead of starting your drawing at T equals 0, you're now going to start drawing at C units to the left. That's your start draw. B controls the adjusted period via the formula period equals 2 pi over, this could maybe be a capital B, but hopefully you understand. B controls the period. And finally, the plus or minus controls your drawing pattern. Which way am I going to draw my period? So how do I do the whole thing? All right, here's an equation. You look at it. Step 1, draw the new center line, whatever D is. Define your amplitude limits using your amplitude. In other words, your max min. Find the period, tuck it away for a moment. You know, your usual start is at T equals 0. Your usual stop is at T equals 2 pi over B. Look for a shift, because a shift determines where you truly will start to draw. Fine. Next, what? Slide either to the left or right with your drawing. Identify where you stop drawing. Here's a good way to look at this. Start draw plus period equals end draw. The start draw T coordinate plus the period equals the end draw T coordinate. You got all those things? You can go ahead and ticky off your Y scale. You can ticky off your T axis scale. And then what's the last thing to do? Draw your pattern depending on where you happen to be. Positive cosine pattern, you would start drawing at your max. If you got a negative cosine pattern, you'll start to draw at your min. If it's a positive sine or negative sine, you will start at the midline, and then you just got to figure out. Positive sine, if that's what you had, you would go up next. Negative sine, you would go down next from the midline. In this light, we sketch the function, and you're good to go. So that's the gist of all of this. I'll have you work on some homework problems. Most of what you've seen here kind of reiterates what we did in class. I really wanted to wrap up this last piece for you as well and give you all the goodies you need to build these types of functions.